Okay, so I just realized there was something I did not tell you about Python. It's kind of important. But when you're writing in Python, indentation matters. So if you're stuck on my other video, it's because you're not following my indentation correctly. So anyway, hopefully that didn't trip anybody up. The indentation matters in Python. Okay, all right. So summation symbol is really straightforward. These examples are pretty straightforward, and it's hopefully a review for most of you. But what a summation symbol means, to use this crazy looking capital Greek S, and in this region below the summation and above and to the right are the magic spots where you put your content. So let's say I have a variable, it could be I or X or anything you want. You have to start your variable somewhere. It could be at 0 or 1, it doesn't much matter. It can go as high as you like, has to be integers. And then you make an expression that has an I in it. Well, if your variable had been X, your expression should have X in it. So let's say I squared. What this means is you can think of this in terms of, it could be a table for you, like a tabular format. I versus I squared, and the I's are 1, 2, 3, 4, 5, meaning the I squares look like so. The summation symbol means we're going to collect up all of these guys and add them. So that means this whole summation symbol with its associated everything should evaluate to 45. Okay? And another concept that is explored in this worksheet is to start making you think about index shifting. So for example, if I, instead of writing it this way, chose to do so, I could say I is equal to 0 to 4, I plus 1 squared, and I would get exactly the same thing, but instead this I would be the gray I, 0, 1, 2, 3, 4, and then this would be I plus 1 squared. But you see, this same column would have the same result because I've done what's called index shifting. I haven't actually changed the value of the summation, but what I've done, and I could sort of do this graphically, I've taken these indices and pushed them down by 1, and then what's inside here, I push it up by 1. Okay, so those arrows have to go in the opposite direction. So if the indices go down by a certain amount and the expression goes up by the same amount, then everything balances out and you're good to go. Okay, so that hopefully that will make sense as you're doing the worksheet. Okay, so I'm just making up this question that's similar to the one that is in your worksheet for question 2. Let's say I want to find the left Riemann sum for area under f from 4 to 8. Now, this function may not look anything like what I'm about to draw, and that doesn't matter. So the point about drawing this squiggly thing is just that you have an idea conceptually of where you're starting and where you're ending up. So that's all we're really trying to establish. We're trying to figure out what the step size is going to do to the number of boxes. So the distance between 8 and 4 is 4, and if the step size is 2, well, you can do 4 divided by 0.2 to get that answer, or 4 times 5, there should be 20 boxes. So if you include the function evaluation at 4 and 8, that's a total of possibly 22 functional evaluations, but as I said, we're always going to leave one out. So if it's a left Riemann sum, we're never going to get to 8, so we're still going to get 21 function evals. So this is why you want to use Python. This is why you don't want to use a calculator. Okay, but how would you write this? How would you write this in using sigma notation? So we're going to think about this. We're going to say, okay, you're going to start at x naught is equal to 4, okay? And then for each of these other 20 evaluations, xi is going to be x naught, which is 4, right? Plus 0.2 times I. So I'm going to start I at 0. I starts here at 0. It's not forced on you, but it is wise for you to start your indexing at 0. Okay? And that will help. And then we're going to want to know, evaluate f at xi. We're going to want to multiply by 0.2, and this is the ith rectangle, or the ith box. So you want to add those all up, okay? And we'll figure out where the i's go in just a second. So but let's just say this. I is going to start at 0. It's going to go to somewhere. It's going to be 0.2 times f of xi. Well, how many i's did we say there were? There's 21 function evaluations, but we specifically started at 0. So we're going to go up to 20. Just realize that if you count from 1 to 20, that's 20 things. So the 0 is your 21st thing, okay? And so this would be your left Riemann sum. Oh, what if the question is the right Riemann sum? How's it going to be different? And there's a couple of different ways you can do that, but you can take advantage of this beautiful indexing here. You can, there's 20 boxes. I'm very, very sorry. I lied to you. There's a 19 because you want 20 boxes. I'm not going to do 21 evals because I'm not going to evaluate both endpoints. Okay, so it's a 19. Okay, so what about if I want to do a right Riemann sum? I'm going to do the easy, lazy thing. I'm just going to go from I equals 1 to 20. And that's why you'll see later in the semester why I was thinking what I was thinking. Let's worry about this one now, I guess. Okay. Okay, so this is your left Riemann sum, and this is your right Riemann sum. Okay? And so you see with the left Riemann sum, we don't evaluate at 8 ever, and on the right Riemann sum, we don't evaluate at 4 ever. Okay. If you want to be more explicit, because if you're going to plug this into Python, you're going to need to be more explicit than that. But I already told you that xi is 4 plus 0.2i, so you're all good to go. And because we're being lazy, we didn't change the indexing system. We just shifted the index itself so we could get the right boxes there. Okay, question 3 and 4 are visual integrals, and the only thing I guess I need to remind you of is what a circle looks like. Haha, only serious. Because what happens is we kind of forget. The formula for a circle, we're used to thinking of it like this, and we forget that we can solve this thing for y like this, and then the top half of a circle looks like this. And then as soon as we write it this way, everybody forgets it's a circle. But if I just wrote it this way, you'd know that's a circle. So just be aware of that. And also for question 4, it's all just visual. Again, you need to know the area of a circle to do that. And another point I need to make, and that's the difference between when a question asks you for integral versus area. So if the area you're looking for is strictly positive, always positive above the axis, then they're identical. And so in order to drive the intuition, we really focus on that. However, you do have to be aware as soon as you start ending up with functions that are like going above and below the axis, you have to be very, very careful whether the question says integral or area. So if it's just they'll say something like the area between the curve and the axis, then you have to split the question like that into 3 pieces, and then you would have to say area 1, area 2, and area 3. And figure them all out and then add them up. But if it just says integral, then you don't have to worry about any of that, and then you can just take the integral and not worry about any axis crossings. Okay, so the exception to the exception here, since what we're doing is visual and it's asking for area, but this is a visual question, let's say you know these areas, so you can calculate, let's say there's a area is 4 here and this area is 4 here, this actually counts as -4 and they would cancel out. And maybe this area is like 5. I don't know, I'm just making that up. So in that case, your integral is going to be 4 minus 4 plus 5, which is 5. So if you're doing a visual question, you have to make sure, if it says integral, that all the area under the axis is going to count for negative and the area above the axis is going to count for positive. If it's an area question, you just have to be very, very careful about how it's worded and follow the intent of the question carefully. Okay, question 5, I'm going to leave you to it, and I just wanted to give you this note. So it's very commonly the case in math that the messier the problem looks on the page, the easier it is for the student. And the reason for 5 being quote-unquote easy is because A, B, and C, and D are all just basically showing you stopping points along the way on a discussion or a proof, and it's asking you to fill in the missing steps. If you are stuck on this question, what you need to do the quiz question is you need to finish E, but you can do E using the result provided in D. So you should think of parts A, B, C, and D as trying to help you think through your logic and how to do proofs in mathematics. And E is just a calculation based off of D. Okay, so if you get derailed, just do part E based on the results in part D, and then discuss it with me in class, and we'll make sure you understand that whole derivation. Okay, see you soon.